It was emerged in the year 1960. And it was further followed by, at that time itself, there were already been 4 generations of ICs. That is the SSI, MSI, LSI, and VLSI, stands for Very Large Scale Integration. So what is meant by this integration? Now we are going to accommodate millions and billions of transistors within a single silicon chip. How is it possible to accommodate billions of transistors within a small chip? We need to keep on shrinking down the dimensions. The dimensions earlier it was thought of micrometer. It has been scaled down and we moved on towards the nanometer technology. You all know what is nanometer, which is 10 to the power minus 9 meters. Not visible. Can it right? That's the dimension of nanometer. So we started off with 180 nanometer technology, scaled down to 90 nanometer technology, 45 nanometer, 20 nanometer. Now, Intel is about to release in terms of 7 nanometer technology. That is the advancement made towards present year. Though we are speaking VLSI, we are already moved into the ultra large scale integration. That is the generation which we are currently in, because of which we are able to realize smart, innovative IoT based products which we are using in our day-to-day life. Being at one place today, we are able to do all the things. Just like moving in a car, we are able to do our office related works and any other works. Well, it's just because of the smart mobile. Hope to handle it, because there is advancement made towards this technology. Right? Okay, let me move on to the agenda. So, already I have given the intro to what we need to go for, micro and nano. Then, what are applications based on microtechnology? Why we move over from micro towards nano? What are the materials used towards this realization? And let's move on to focus on the applications. When we speak about various applications using this micro and nano, there are going to be certain drawbacks as well as demerits. And what is the future trend towards this nanotechnology, followed by contribution and preference. Micro, as I already told you, it involves the design, the creation of the system or the components which are going to be very, very small in size. And we want to realize the products which are highly accurate, very highly precise, which is about the dimension of 10 to the power minus 6 meters. When we speak about this micro technology, the mechanics is much larger than compared to micro. Micro is much larger than compared to the nanotechnology. And with respect to these technologies, it's not that we are focusing only towards electronics. We need to think about various other systems involved in. One is mechanical, electronic, optical, and computing elements. So the various sectors where we can employ this microtechnology, the objective of today's system design is we want to realize the system that is going to be very, very smaller in size. It needs to operate at a higher speed. That is, today we want to operate at a bigger speed. And you want to achieve the size of the chip should be very, very small. You want to achieve all this at a minimal cost. The power consumed by these devices also should be very, very minimal, because everything is portable. It's a battery operated. If I want to retain the charge that right of the battery, the power consumed by the device should be very, very minimal in order to reduce the recharging time. And these are the various sectors of this microtechnology. The very best example we can give is the smart mobile phone. The very first one was introduced, the mobile phone was introduced in the year 1973 by Motorola, but at that time the phone size was too big and also cost is very, very high. The battery life was about just 20 minutes. units. Just imagine, can we live? Today, is it possible to live without the very first thing when we are about to step out of our homes, whether we have taken our mobile phone or not? That is the first thing, right? Especially the students, today's students. So the mobile phones are more and more compact. They are able to do more smart operations we are able to do with our mobile phone, and without this Microsoft technology, today we cannot imagine this type of. So why are we to go towards the nanotechnology? There are two important things that we need to discuss. One is the size, the physical size. We want to still compact the size of the chip, the system which you are trying to use, and also the cost involved in microtechnology towards the fabrication is huge. So as we keep on shrinking down the size, it is possible to bring down the cost involved in the fabrication of integrated circuits. So these are the two main reasons why we are moving towards the nanotechnology. So nano, in order to meet the vital needs of every human to lead a sustained life, nano is going to be the best solution to, we all know what are the vital needs for shelter, clothing, and to have a healthy and very good environment. To achieve all of this, nanomaterial is going to play a crucial role. And due to the various efforts that have been put forth by the researchers over the last 30 years, I think we are able to do a very good progress in terms of the various technologies. Starting from the smart agriculture, various revolutions have taken place in the food technology, and for water purification, for energy storage devices, chemicals, and as well as in cosmetics technology, health, medical electronics, wearable electronics, sensors, nanosensors, smart sensors, everything is achieved today because of the efforts put forth by the research. So nanotechnology, when we speak about this nanotechnology, you are going to be involved atomic, molecular, and supramolecular level. That is, because it's very, very minute in nature. So it's going to operate at a supramolecular level. Though we say it's about 100 nanometers, we want to shrink down towards 20 or 7 nanometers to meet out the two. So the nanometer already I told you is about 10 power minus. So the point that nanotechnology, it was introduced by the researcher Murillo in the year 1974. The very first nanomaterial founded by Richard Feynman. He is the founder. See, today, whatever the logic gates that we are using, conventional logic. But using nanotechnology, we need to move towards quantum computing. It is not based on conventional logic. It is going to be based on reversible logic. You cannot make use of and or our gates. You have to move completely. The conventional basic logic gates need to be replaced by reversible gates. And here, the one who proposed first reversible logic operation. In the year 1980, he proposed it, and he has also discovered the very first nanomaterial, carbon-based nanomaterial around 1985, which is 360. It's the very first, which is highly used in today's nanotechnology design. So you are quite familiar about this macro, which is visible with our eye. That is the example for micro, which can be visualized through the microscope. What is a very good example we can give here is what we see. And nano, so a specialized microscope, the example is visualized material. This is the nanometer scale, another example. So in order to realize the design, using this nanotechnology. You need to be expert in all the disciplines, engineering as well as chemical kinetics, physics at a molecular level, and the biology when we move towards the application of nano towards the clinical and the commercial application. So USA, the National Science and Technology, they actually claim that nanotechnology is going to play a crucial role, especially in the coming decades. It is going to change the name of almost every object that we are using today, day-to-day life. And these are various sectors, nanomaterials applied already. Some of them we are using, and most in some of the applications are still at the research level, and it's going to make a $1 trillion market where if so these are the fine, especially related to health, it's going to play a crucial role, and for flexible electronics, for wearable electronics, we are going to have a crucial application of nanotechnology. These are the other things or products which we can really. So in order to achieve this, the first thing is we need to realize the nanostructure. How to realize it? There are two different approaches to come with the nanostructure. One is top-down, the other one is bottom-up. Same as like system design. In whether it of development or embedded system design or any system design, if you want to design anything, there are only two approaches, top-down or bottom. Top-down is start at the system level, then keep on move towards the next sub-levels, and finally the lowermost level of the system. Whereas bottom-up phase will start with lowermost level, then you will keep moving towards the next upper level, and finally all realize the same approach here also. In order to realize the nanostructure using top-down approach, you start with the whole white substrate. You need to keep on cutting down them into so many clusters. That is called as fragment. That fragment is further sliced and it will end up with a nanostructure. That is top-down. Whereas bottom-up is, you will be having so many atoms. These atoms need to be piled up one over another, into a cluster. The clusters are the different types of nanomaterials. So in order to make use of, to realize the system design, the fundamental that you need to employ is the nanomaterial. This can be classified into four types. One is carbon-based, the other one is inorganic and organic-based. The last one is composite-based. Carbon-based, as the name implies, the fundamental element is it is based on carbon-based nanomaterial, and it's going to be available in three different structural forms, either tube-based or helicoid-based or chemical-based. And these are the fundamental carbon-based nanomaterials. One is graphene, then fluorine, carbon nanotubes, then graphene's derivatives, and so on. Of which graphene is the most widely based nanomaterial, and it is highly employed in the realization of flexible electrons. Inorganic based means it is based on metal and metal oxide based nanomaterial. When I say metal and metal oxide, under the metal gold nanoparticles which are employed to detect the pathogens in our body, to detect the presence of any unwanted bacteria or virus. For that, we can make use of this gold nanoparticle which is employed for medical applications. And also lanthanide series, you might have studied in your chemistry periodic table, lanthanides and anthanides. Lanthanide ions, which is paramagnetic. Under that there are two cases, paramagnetic and dimagnetic. Paramagnetic means when we move from one energy level to another upper energy level, if there is no electron pairing occurs, it is basically considered as para. Dia means it's the reverse, when electron pair occurs. that particular lanthanide series plays a widely employed. The other one is organic based nanomaterial. The materials which does not come under organic and carbon based is basically organic, and these are naturally available nanomaterials. One is ferritin, iron based component, which is available in our human body also, that is liposome, dendrinos, missiles. All these are naturally available nanoparticles. And the last one is composite based nanomaterial. So already composite based, you need to create a larger how to achieve this a larger nanomaterial. Already you will be having one phase of nanomaterial, upon which you need to combine another nanomaterial, using which you are going to realize a composite based nanomaterial. So these are the different types of nanomaterials which can be employed to realize nanotechnology. So when I spent in the previous slide, we were talking about the carbon nano. So first part of the structure of carbon nanotube. The one is aerogel, and nanoparticle is going to look like that. That is the one in the last. And the scope is already I told you, it can be employed for flexible, for wearable device, and at the molecular device system level, you can widely employ it. So in order to make use of this nanomaterial for wider applications, the fundamental principle behind the nanomaterial is it is super hydrophobic. What do you mean by this super hydrophobic? It is water repellent. It's just lotus leaf. Basically represents a lotus leaf, and it has antimicrobial feature which helps it to swiftly. And also for biofueling applications and all, you can make use of this nanomaterial. Because of the structure, it has got a waxy coating by means of which it can self-clean it. And super hydrophobic means, already told you, it has a water repellent one, which means water will, when you just slide it off, water rolls up. The water droplet remains on the leaf, it is going to be always round in shape. That is the fundamental principle behind this super hydrophobic. And it is non-polar in structure. There should not be affixed towards the polar concentration, and water rolls off whenever the surface is held at an angle, and the contact angle should be always greater than 150 degrees in order to achieve or satisfy the principle of nanomaterial. So let's move on towards the application. First, let us discuss about some of the applications achieved for flexible electronics. So to use nanotechnology or nanomaterials for flexible electronics, we need to realize the electronic component. That is the very first thing is the nanotransistor. So in order to understand the principle, one should have a thorough understanding on the interaction atoms and molecules at the supramolecular level, that is in terms of nanometer. And since its dimension is going to be very, very small, you can realize the chip which is going to be much smaller in size, and also the nanomaterial, it has got very, very higher electron density. Why? Means that is the basic principle or the structure of whatever the nanostructure that you are going to employ, whether it is a carbon nanotube or ellipsoid or spherical based or honeycomb based lattice structure, it is going to be highly uniform and symmetrical, because of which it is going to offer a very high electron mobility, by means of which the speed at which the system is going to operate is going to be very, very superior in nature. So that is the fundamental principle. You can achieve a faster frequency. Operational speed is going to be much higher when we employ nanomaterial for electronics design. So these are the things which can be realized: nanotransistor, nanodiodes, and organic LEDs. Nanomaterials can also be employed for plastic space because it is very, very small. It cannot be visualized through the naked eye. So it can be used as a conducting in between. So for